Hello and welcome. This is a lesson on differential equations. This will be a crash course. We're going to do not a ton of stuff. Normally this unit would take about 4 blocks, but we're going to do it in 2. We're just going to give you an overview. You will revisit differential equations if you choose to take analysis 2. So there is still the opportunity to get a lot more difficult if that's something that you're interested in. In this video, we'll define what a differential equation is. We'll solve a first-order differential equation, maybe 2. This is more of an excuse to get practice with integration, to be honest. And then we'll look at what do you do when you can't solve a differential equation. Sometimes it's difficult to solve, sometimes it's impossible. And 2 ways we solve differential equations that are impossible are with Euler's Method. Hashtag Ms. Piper. Hashtag your freshman year. And with slope fields. So we're going to look at those. Just so you are aware, in the Larson textbook that we are using, you will find a lot of this content in chapter 6. Because we are doing a crash course, we will be bouncing around a lot. For example, slope fields are in chapter 6.1, and solving separable differential equations is in chapter 6.3. So this is going to bounce around a little bit, so I just recommend skimming through that textbook, reading in detail if you're confused, but just giving it a once-over to see if it helps make things make more sense. With that said, though, let's go ahead and get started. Alright, so to get started, the first question I have for you is, what is an equation? Think about that for a second. What is an equation? An equation is a statement that 2 expressions are equal. So let's say I have the expression 2x plus 5, and I have the expression 10. An equation is, it kind of looks like a 16. Whoop, there we go. All right, an equation is when 2 expressions are equal. A differential equation is an equation that has a derivative in it. A differential equation is an equation that contains a derivative. All right, you've seen a few differential equations before. Here's an example. Y prime is equal to x squared. Some other examples. Dy dx is equal to x cubed times y. All right, that one's a little bit different. Right? Here, this looks like what you've seen before. It's just the derivative with respect to x. Right? But over here, we have the y function in the derivative. So that is going to be the thing that kind of sets differential equations apart from what you've done in the past. You've dealt with equations that have derivatives in them before. But now we're going to start looking at derivatives that not only contain a derivative and the variable x, but also the actual function itself. So the function and the derivative exist in the same equation. I got 2 more for you. We got dy dx is equal to x squared times the square root of x. And then we also have, here's another one, dy, and these are all examples. Right? These are not all the differential equations. X plus y. Or this should be a y. I think I said y, but I didn't mean to write an x. All right, the reason why I bring up these 4, right, 1, 2, 3, 4, is because we're going to solve these first 3. We're going to figure out solutions to these first 3. This 4th one, it's a little bit harder actually, and we're not going to solve it. But we are going to talk about how you might solve it versus how you might interpret this differential equation. Right? The fact that there's addition here makes this a little bit more hard. Before I move on, though, I just said that there are solutions to these differential equations. What is a solution to a differential equation? Like up here, the solution is, what would that be? 2.5, 2 times 2.5 is 5 times 5. So the solution here is equal to 2.5. What is a solution to a differential equation? Right? Well, we are going to have families of solutions. Because there are lots of functions that when I plug them into this, I get the derivative is x squared. We got 2x. We got 2x plus 1. Sorry, not 2x. Let me rewind. We got x cubed divided by 3. There we go. Right? We have x cubed divided by 3 plus 1 plus 12 plus 123. Whatever number you want to add. So there's a family of solutions to this first one. And I was able to look at this and just know the solution. These are a little bit more difficult to find solutions to. But for this one, x cubed over 3 plus c, that is our family of solutions. And let me just add a y here so I can clarify. This function, f of x, let me actually, instead of writing y, let me write f of x. Right? This function here works in this equation. If I plug this function into this equation, and meaning I take the derivative and plug that in for y, I will get a true equation. Right? If I plug in 2.5 up here, I will get a true statement. Right? 10 is equal to 10. If I plug this function into this equation, I will get a true statement. So let's go ahead and look at number 2 on the next page. dy over dx is equal to, let me just go back and grab it. We got x cubed y. Cool. So how do we solve this thing? How do we find all the functions y equals f of x? How do we find all the functions y equals f of x that satisfy this equation? So that when I plug it in, I get the derivative of this function is equal to x cubed times the function itself. And the way we do this is possible because this equation is a separable differential equation. Now, what do I mean by that? Right? This equation, I am actually able to isolate all the y's on one side and all of the x's on the other side so that I have an equation. Let me go ahead and do this. I'm going to divide both sides by y. Right? I get dy over dx times 1 over y is equal to x cubed. And I'm going to do something that is generally frowned upon in math, but I'm going to rewrite, I'm going to multiply both sides of this equation by dx. Now remember, dx is not actually a number, right? But what I'm going to do, this is the name of what I'm doing. It's called rewriting in differential form. Right, so what I'm about to do is going to look like multiplying both sides by dx. Right, but I'm going to rewrite this equation in its differential form. So I have, and I'm going to use the commutative property of multiplication to write the 1 over y in front of the dy. And then I'm going to write x cubed dx. Now you can look at these and kind of agree with me that they are the same equation. All right, it's almost like I multiplied both sides by dx. All right, but I'm rewriting this equation in its differential form. I have separated the variables. All right, we have 1 over y dy, and we have x cubed dx on separate sides of the equation. Right? This is the key to being able to solve separable differential equations. All right, the previous page, let me go back. You might start to think about why this equation number 4, why it's not separable, and why it might be a little bit more hard to solve. Right, but let me go back. All right, we're here. Right, the separable differential equation. And what I'm going to do is I'm going to integrate both sides. Right, I'm going to integrate the left-hand side with respect to y, and I'm going to integrate the right-hand side with respect to x. What's the antiderivative of 1 over y? All right. That is the natural log of the absolute value of y, right? Plus some constant, right? Put a c1 because I'm seeing the future a little bit. Let's go ahead and integrate the right-hand side. All right, that's going to be x to the 4th divided by 4, all right, plus some constant. Right? And you may be asking yourself, why do I have 2 constants when I could just absorb them into 1? And that's what I'm going to do next. All right, let's go ahead and rewrite this equation. This differential equation, right? Actually, this is not a differential equation. This is the solution to a differential equation. No derivatives in this. All right, and I'm going to combine those two constants into one capital constant. Cool. So I integrated. I got some equation, right? But I do not have a function y that when I plug into this equation, I get a true statement. Right? I am solving for a function. Right? The solutions to this are a function. We need to find y. We need to isolate y. So how do we solve this equation with a logarithm in it? Well, we know the base here is e. So let's, as Mr. Schaefer would say, e it up. All right, we're going to raise both sides to the base e. All right, e to the ln of y, that is going to be the absolute value of y. And then over here, I'm just going to get that. I'm going to get e to x over, to the 4 over 4. And then plus c. And then I'm actually going to go over here, just because I don't want to do a whole new page for this. Right? E to the x over 4, x to the 4 over 4 plus c. Right? When I have addition in an exponent, I can turn that into multiplication. Let's go ahead and do that. So here is our solution. Right? And I'm actually going to put that e to the c. And if you think, hey, isn't e to the c, where c is a constant, just a constant? Boop, boop. Let's go ahead and write it as constant. E to the x to the 4 over 4. This is our solution. Or I could say family of solutions, because this is just the form of any function that does work with this original equation. Right? This is the form. No matter what a is, it's going to satisfy this equation. All right, before I proceed to the next example, there's two things I want to do. I want to check and see if this actually works. Right? When you do factoring, back in factoring camp, one thing we like to say is that solving factoring problems can be difficult, but checking your answer is not. Right? Solving differential equations can be difficult, but checking your answer isn't necessarily. Right? It's as hard as whatever derivative you're taking, because all we got to do is take the derivative of y here, and then plug everything that we know. We know y. We'll know the derivative of y. We got x cubed there. Is it a true equation? So all we got to do is plug it in. Or the other thing I want to do is I want to address these absolute value bars. All right. I'm just going to go ahead and casually get rid of them. And I want you to think about why I can do that. Right. It has to do with this constant. And it's a constant. Maybe it's positive. Maybe it's negative. Right. Maybe some initial condition that solves for that a will address whether it's positive or negative. Right. So I can go ahead and get rid of those absolute value bars because this arbitrary constant is either positive or negative. We don't have enough information to know yet, but we can go get I'm losing my words. We can get rid of those absolute value bars because this is a constant. All right, let's check on the next page if this is actually a solution. So let's go with light blue. That's fun. All right, so we have the differential equation dy over dx is equal to x cubed times y. Right? We established that y is equal to a e to the x to the 4th over 4 is the family of solutions. We had a constant, but it got absorbed into the coefficient here, right, as e to the c. Let's go ahead and see if this actually works. So we have y. We just need dy over dx. We need to take the derivative of this. So the derivative of this thing is the derivative of e to the x to the 4th over 4. That's just going to be, well, let me keep that constant there. E to the x. All right, we're just going to, that's the power of e. It's the same thing. But then we got to chain rule this thing. Let's not forget that. The derivative of this is, bring the 4 down, 4x cubed divided by 4. Those 4's go away. And then we have dy over dx is equal to a times x cubed times e to the x to the 4th over 4. All right, let's plug all this stuff in. Right, dy dx, that is a x cubed e to the x to the 4 over 4. We have an x cubed there. Okay. And then y is a e to the x to the 4th over 4. and then just doing a little bit of moving around, we can verify that these are the same expressions. Right? What is an equation? Two expressions that are equal. Ax cubed e to the x to the 4 over 4. Smiley face, check mark, star, whatever floats your boat. This equation is valid. This is a valid solution to this differential equation. So what do we do real quick? We moved all the y's to one side and the x's to the other side. In this case, that wasn't much algebra. Right? Then we rewrote this equation in its differential form. We moved this dx to the right-hand side. We integrated both sides with respect to their respective variables. So over here with y, and well, not down there, but here, we went here. Let me make sure I circle that c. And then over here, we went there. Right? And in doing this, we then solved for y, got rid of some absolute values because that's valid in this scenario, and then we verified that our solution works, right? Let me get back. There we go. We verified this equation floats our boat. All right, let's do a few more examples, and then we'll jump to how to deal with that one that was not separable. Okay, here is my example number 3 from the previous page, or the page from a while ago. All right, step 1. Let's isolate the y's and isolate the x's. All right, in this example, that just means I'm going to write this as dy dx times 1 over the square root of y is equal to x squared. All right, halfway there. I'm going to rewrite this in differential form. So I have dy, and I'm going to go ahead and write that square root 1 over square root y in front of it. And then I'm going to write this as x squared dx. It looks a little bit like cross multiplication. Right, but we're going to be a little bit more careful. We're rewriting this in differential form. Now we're going to take the antiderivatives of both sides. Right? Over here, this is no longer the natural log. This is going to be, well, let's do it on the side right here. I'm going to write this as y to the negative 1/2. All right, we're going to raise that to y to the 1/2, divide by negative 1/2. We're going to get negative 2 y to the 1/2, right? Plus c. But I'm not going to write that plus c because I'm just going to add that plus c on this side over here. This side's going to be x cubed divided by 3, and then that's where I'm going to write my plus c. All right, we are on our way. All right, we have not finished though. We need to solve for y. So let's go ahead and divide everything by negative 2. We get y to the 1/2 is equal to x cubed divided by negative 6. Right? Still plus some constant, because a constant divided by negative 2 just a constant. I mean, this constant is going to stay floating. We'll discuss what we do with it later. Right? And then we're going to square both sides. And we are done. Y is equal to x cubed divided by negative 6 plus c quantity squared. Let's see if this is a valid solution. All right, let's plug it in. Let's take the derivative of y. I'll do this in a different color. Let's go with orange. All right, that's like a blood orange, delicious blood orange lemonade at what's that pizza place called? Blaze. Yeah, get some of that red orange lemonade. It's so good. All right, so the derivative of this, we're going to bring that 2 down. Everything stays the same in the middle. All right, then we take the derivative of the middle. This is just the chain rule. It's going to be x squared divided by negative 2. All right, cool. Looks like there's some simplification that can go on there. But this is going to be equal to, well, we're trying to verify that it is equal to x squared times the square root of y. And where is our y? It's right here. Right? X cubed divided by negative 6 plus c squared, all square rooted. Right? Those square roots are going to disappear. And we're going to get, it looks like, boom, boom, boom. We have negative x squared, x cubed divided by negative 6 plus c. That is equal to x squared times x cubed divided by 6 plus c. Running out of room right there. All right, it looks like I did something wrong because this is not negative on this side. This is negative on this side. Let's see if I can find out where I made a mistake. think I made a mistake here. So you guys have probably been screaming for the past, you probably like filled out the form and told me that I was wrong here. Yeah, because I raised it to 1/2. I should have divided by 1/2. All right, and that's going to make this a positive 2. And then over here, I'm going to get a positive 6, and then this is going to be, that's going to be a positive 2. That's going to be a positive 2, still cool. This is going to be positive. Look at that. All right, this is a solution. These should also be positive. Very sorry about that mistake. I'm not going to go back and fix it. My bad. Regardless, we have found ourselves a solution to this differential equation. A family of functions. Family meaning that there's that constancy that can be whatever it really needs to be. We found a family of functions that satisfy this differential equation. All right, it's time. dy over dx is equal to x plus y. All right, maybe you've already thought about it. Why is this invalid? Why, not invalid, sorry, let me take that back. Why is this not a separable equation? And why can we not solve it by the means of what I've been doing? Well, if I move the y to the left-hand side, dy over dx, I'm going to have a subtract y, and then an x on this side. Then if I try to write this in differential form, it's going to be dy minus y. Oh, the y gets hit with that dx as well. Right? We have an issue here because I now can't integrate both sides with respect to their respective variables. Right? There is a way to solve equations like this. We're not going to look at that in this class. This is an inseparable differential equation. Right? But we will look at how to approximate solutions to this curve using something that you have done before, the Euler Method. All right, think back to 9th grade when you did this with Miss Piper. I think it was on your graphing calculators, your TIs. Right? We're going to revisit Euler's method and see how it's useful here. Because if you remember, Euler's method was all about slopes. We have that. And points. We have that too. Right? We can use Euler's method to interpret this equation. All right, before we do that though, I do want to revisit our equation number 2 and talk about something called a particular solution. Right? We have solved these, well, not all of them. We have solved the first 3 separable differential equations by rewriting in differential form, integrating, and then solving for a family of solutions. All right, what does it mean to find a particular solution? All right, we have an infinite amount of solutions. What if I want one? All right, what does that even mean? How do I know which one I want? All right, let's look at that. So we had dy over dx is equal to x cubed times y. Right? We had the family of solutions. Y is equal to a times e to the negative, sorry, not negative, to just the x to the 4th divided by 4. Right? This was our family of solutions. Well, what does this look like? All right, this graph, a times e to the x to the 4th divided by 4, looks like this. All right, but that's if we have a value for a. Like maybe it looks like that, maybe it looks like that. Right? Maybe a is negative and it's down here. Right? This is all the possible graphs of solutions to this differential equation. Well, the way we solve this for a particular solution is that we are given another piece of information, like almost always. Right? We are given an initial coordinate. For example, I want a solution to this differential equation that also satisfies the initial condition. And I'm actually going to write condition here instead of initial coordinate. Condition. I think I spelled that right. Let's say that we are given the initial condition that this solution also satisfies the coordinate 0, 2. All right, so how do we solve for A? We plug this thing into our solution, and that'll tell us what A is. So y is 2. Right? We don't know what A is. E is E, and then x is 0. So 0 to the 4th divided by 4, that's just 0. All right, e to the 0, that's just 1. And it looks like A is 2 in this example. All right, so the particular solution to this differential equation, here's the family of solutions. The particular solution is y is equal to, we just established that A is equal to 2 times e to the x to the 4th divided by 4. There is our solution. And this of course works. We already verified that it works for all values of A. Right? But this equation here also satisfies the extra condition that 0, 2 is on our graph. And I believe that 0, 2, or sorry, y is equal to 2e to the x to the 4th divided by 4 is, well, it certainly is. It's going to be one of these ones in the upper half of the coordinate plane. All right, so let's just pretend like it's this one. Right, when I plug in 0, I'm going to get 2. So let's pretend like this is 0, 2. Yeah, sweet. Okay, we have so far solved separable, why can't I not say it? Separable differential equations. And we have also found a particular solution, a single solution of the family of solutions that satisfies two things, both the differential equation and an initial condition. Let's look at what happens when we cannot solve the differential equation, or we can. Let's see a technique that is used to solve differential equations approximately. Euler's method. So let's give ourselves a quick graph. All right, let's pretend like we're given a differential equation, right? Slope as a function of x and y. And let's say the actual solution to this contains the point 2, 4. And the actual solution ends up looking like this. Cool. Right, this is a function who satisfies this equation here. All right, what do we know? We know that when I plug in the coordinate 2, 4, it's going to output a slope, right? And that slope is going to look like this. And then if I use this slope to then get a new point, I can do the same process. Right? If I can find out what this point is right here, then I can plug this coordinate, let's call it 2 plus delta x, comma 4 plus delta y. I can plug this point into the function and get its own slope. I can get a new slope. And then I can use that slope to approximate the curve. And I can continually do this for as many times as I need to approximate this curve. Now you'll notice that as I continue to get a new point, I'm slowly getting further and further away from the actual curve. Now that is just what happens when you approximate a curve using the differential equation. It's not going to be perfect. How do we make this curve better? We draw smaller tangent lines. Now, of course, this is going to eventually get off of the actual curve, but it's a little bit better. And if we make these partitions even smaller, we're going to get a better and better approximation. This is the Euler method. This is kind of a review. You did this when you were in 9th grade, right? So how can we streamline this process? How can we find values out here given an initial point way over here, and then using the fact that we could solve for the slope at points within the Cartesian plane? All right, so let's say we have the differential equation, x plus y. And let's go ahead and say that 2, 4 is a coordinate on this differential equation's solution. All right. So what is the coordinate? Sorry, what is the slope at 2, 4? All right, what we do is we plug 2, 4 in. So if you plug 2, 4 in, you get the slope at the coordinate 2, 4 is 2 plus 4, which is 6. Cool. All right, so at 2, 4, we have a slope of 6. All right, now we need to decide on an increment. How far am I going to go to the right? Let's, in this case, go, let's make our delta x 0.25. Right? Now we need to figure out what is our delta y. Well, delta y over delta x is 6. That was a weird 6. Multiply both sides by delta x, and delta y here is 6 times delta x, or 0.2 times 6, which is 1.5. So I'm going to go 0.25 to the right and up 1.5. All right, let me get rid of this. All right, and then now I have this new point. What is this new point? Well, this new point is delta, it is, sorry, 2 plus delta x, comma, what is it, 4 plus delta y. All right, what is that? Well, we have delta x. Delta x was just predetermined. It's our increment. And delta y ended up being 1.5. It's just delta x times the slope. So it ended up being 1.5, 4 plus 1.5. And the new coordinate ended up being 2.25, comma, 5.5. All right, now we can proceed. We can do this process again. We're going to use this coordinate now, which is 2.25 times 5.5, and proceed. Right? This is a lot of math. Let's try to put this in a chart and make it really easy to follow. All right, so I need an x column. I need a y column. I need a delta, not delta. I want a dy over dx column. I want a delta x column, and I want a delta y column. Right? This chart right here is going to be my best friend. My differential equation was dy over dx is equal to x plus y. Right? My initial point was 2, 4. So 2, 4. All right, my dy over my dx, that's going to be 2 plus 4, that's 6. My delta x is, in the example I was doing on the previous page, 0.25, but this can be whatever you want. If you want to be more accurate in approximating the solution to this differential equation, then you'd want to make this number smaller, maybe 0.1, maybe 0.05, maybe 0.000001 if you're using a calculator, hint, hint. All right, but for this, just for the purposes of showcasing the Euler method, I am going to use 0.25. All right, and what is y? Well, that is, I'm just going to write it here. It is dy dx times delta x. Right? It's the multiplication of these two numbers. What is that? Well, that's 1.5. We already calculated that. All right, so what's this next row going to be? Right? Well, what is x? Well, what's the next x? Sorry. Well, that's just plus this increment, 0.25, and that's always going to be the case. So this is 2.25. Then what's y? Y is this number, right? 4 plus this number. Sorry. Right, that's why we're setting this chart up so we can establish the next y value. That's going to be 5.5. 4 plus 1.5. All right, what's dy dx? Well, now that I have x and y, just plug that in. So that's going to be 5.5 plus 2.25. That's 7.75. Right. What's delta x? 0.25 again. That is the chosen increment. And then what is delta y? That's going to be the multiplication of these two numbers, which is I did it in advance. That's 1.9375. All right, let's continue, right? I am using the differential equation and Euler's method to establish other coordinates on my graph. All right, so let's say I want like 3. I'm going to have to do this to 2.5, 2.25, 2.5, 2.75, 3. And yes, this feels like it might take a while, and by hand it does, but this is obviously something that you can tell a computer to do. So I'm just going to do it really quick. I'm going to add all the values, and then just to show you the process. Boom. And the magic of video editing, there it is. All right, so we started at 2, 4. All right, plugging that into our differential equation that relates the derivative with the values. We got 6 as our slope. All right, our increment was 0.25. That was chosen. And then that caused an increase in the y by 1.5. Right? Those two numbers there, delta x and delta y, gave us these two numbers. And then these two numbers gave us our slope. Our increment was chosen. These two numbers then gave us our new delta y. And then this delta x and this delta y changed these numbers. And then we proceeded this process until we got to the coordinate 3, 13.0898 ... Right? And this is a method that we can use to approximate the solution to this equation given an initial condition. This is the Euler method. Now, but notice, every single point in the coordinate plane has a derivative associated with it. Right? This leads us to another type of way to look at differential equations, and that is slope fields. What is a slope field? Well, give yourself an xy plane. We are going to graph at every single lattice point. What a lattice point is, a integer coordinate. All right, so I'm going to go up to 5, and this is actually going to take me a second, so I'll fast forward in the video later, the editing post process. All right, fast forwarding over. This is these are the lattice points from -5 to 5 in both the x and y directions. What a slope field says, or does, or has us look at, is what is the slope given the differential equation dy dx as equal to a function of x and y? Right? What is the slope at all these points? And as we start to literally graph a small little slope at every single one of these points, we will see the family of solutions to the differential equation. So what we're going to do here is we're once again going to look at dy dx is equal to x plus y, fairly easy one to just pump out. And let's look at what the slope field looks like given this as our differential equation. Okay, so what is the slope at, say, the coordinate -1, 1? Right, -1, 1 is right here. What is the slope here? Well, at -1, 1, we plug in -1 in for x, 1 for y, and we get 0. So at this, I'm going to draw, and let me delete that stuff. I'm going to draw a small little slope of 0. Let's look at another point. Let's look at -1, 2. At -1, 2, I'm going to get a slope of 1. So I'm going to go ahead and graph a slope of 1 right there. Right? At -1, 3, I'll get -1 plus 3, which is 2, even a little bit steeper. And you'll notice then I get 4, then I get 5, and I have now done 5 of these. Right? It is now time for me to do all of them. And there is a much faster way to do this, but I'm going to do all of them. And I'm going to fast forward through it so that I'm not killing your time. All right, and I am done. All right, so you can kind of see what's happening here. I can look at approximate curves that go through certain points. Like, for example, we looked at 2, 4 earlier. 2, 1, 2, 3, 4. Right? The slope there was, I believe we said it started at 6. Right? And as we got bigger and bigger, our slope, so it was shooting up like this. And if we were to look at it the opposite direction, it would kind of do. Eventually it would hit 0, and then it would turn back around. Right? We can kind of see this is the curve that goes through the point 2, 4. Right? This is the particular solution to dy dx equals x plus y with initial condition 2, 4. All right, but I could do this with any single point, right? I could, let's go with a new color. I could pick this point, and what would happen? It would do something like this. And there's this very unlikely solution right here, and I'm kind of getting off of it. Sorry about that. All right, if I change my initial point by just a little bit, if I start on any coordinate that's on this purple line here, it's going to follow this path. But if I change it slightly, like it's going to follow this path until it starts to peel away. All right, we call that an unstable differential equation. All right, any point, if you change it a little bit, it's going to diverge from this straight line. All right, so, and I can keep doing this. Right, this is the family of solutions, and particularly this green one was the solution that we were looking at before with Euler's method. This is a slope field. So if you are feeling a little bit lazy, or you're just a normal person and you don't feel like drawing your own slope field, there is a website called mathgraphs.com. And this will give you the slope field for all the problems in the Larson textbook. So when you're doing your classwork, Larson's textbook, the slope fields can be found online. For our textbook, go to this website and go to Calculus ETF. You'll see at the top several textbooks. Go to the one labeled Calculus ETF and go to edition 4E. Then go into this section of the textbook that the problem exists, and it will give you the graph of the slope field to save you some trouble. All right, and there it is. We're going to stop here. But what did we look at? We looked at differential equations for the first time. And once again, if you want to learn more about differential equations past what we do in this video and in Mr. Schwartz's video, we have a whole class, a whole a semester dedicated to differential equations. The second half of analysis 2 will cover differential equations in depth. But here we define a differential equation. It's just an equation, like you know it, two expressions that are equal to each other. But one of those expressions or both those expressions have a differential equation. And we didn't look at second order differential equations. We've only looked at first order. Right? Second order is if there's a second derivative in there. And you can keep getting further and further and further down. A third, 4, 5, 6. We solved some differential equations. We looked at some easy ones, so we can certainly make those integrals more difficult. But there are some differential equations that we just cannot solve. And when that happens, we can look at the solutions using the Euler method. We can use an initial condition and kind of learn about other points approximately using the Euler method. And then we can also use slope fields to visually look at the solutions. And then graph all the possible slopes and then find our curves within those slopes. This, once again, is in Chapter 6. And I am going to end the video now.